There is a number that every ocean scientist on Earth has been watching since January, and as of this month, that number crossed a line it has not crossed in 2 years. It is a small number. It sits at 0.5 degrees Celsius, and it is the official signal that the Pacific Ocean has changed state. The number comes from a place in the ocean called the Niño 3.4 region. That is a specific box on a map, drawn by NOAA more than 30 years ago to be the official measurement zone for tracking El Niño. The box sits in the central equatorial Pacific. It runs from 5 degrees north of the equator down to 5 degrees south of the equator. It runs from 120 degrees west longitude over to 170 degrees west longitude. That is a strip of open ocean roughly the width of the continental United States. It contains no land, it contains no major shipping lanes, and it is monitored every single week by an instrument network that took NOAA decades to build. Inside that box, scientists take the temperature of the water at the surface day after day from satellites and from a chain of moored buoys called the TIO array. Then they average those readings over 3 months. Then they compare that average to what is considered normal for the time of year. The result is a single number called the Oceanic Niño Index. The Oceanic Niño Index is the official scoreboard for El Niño. For the March, April and May season of 2026, that scoreboard reads plus 0.5 degrees Celsius. That is the line. NOAA drew it decades ago, and they drew it deliberately. Anything below plus 0.5 is considered neutral. Anything at or above plus 0.5 sustained across several 3-month seasons is considered an El Niño in progress. The Pacific has been sitting below that line for 2 years. As of the most recent reading, it is no longer sitting below it. It is sitting exactly on it. There is a second number, taken on a faster schedule. NOAA publishes a weekly reading of the Niño 3.4 region as well, not averaged across 3 months but updated every 7 days. That weekly reading currently shows plus 0.4 degrees Celsius. It is the most current pulse from the Central Pacific. It is slightly below the official threshold, and it is the reading that some forecasters watch most closely between the monthly updates, because it tells them which direction the seasonal average is heading next. 2 numbers, both small, both on their own, easy to dismiss. A few tenths of a degree in the temperature of a patch of ocean water does not sound like a planetary event. It does not sound like anything at all. That is the problem with the way these numbers get reported. Because there is a third number, and the third number is the one that does not fit the calm picture. NOAA also tracks a region called Niño 1+2. That box sits much further east. It is pressed against the coast of South America, off the shore of Ecuador and northern Peru. It is the smallest of the official Niño monitoring boxes, and it is the one closest to land, closest to people, closest to the fishing fleets and the coastal cities that have lived inside this cycle for generations. The Niño 1+2 region is currently running at plus 1.0 degrees Celsius above normal. That is double the threshold. That is twice the value of the Central Pacific reading that the headlines are quoting, and it is happening at the exact stretch of coastline where the worst destruction of the 1997 to 1998 El Niño took place. The warming signal has reached the coast first. It has reached the coast harder, and it has reached the coast while the official Central Pacific scoreboard is still sitting right on the threshold, doing nothing dramatic on paper. That asymmetry is the part of this story that is not being told. The central reading is the one the country hears about. The coastal reading is the one that is moving fastest, and the coastal reading is moving fastest in precisely the place where this same mechanism produced its most catastrophic damage in living memory. A scientist looking at these 3 numbers together sees something different from what a viewer sees on the evening news. The viewer sees a plus 0.5. The scientist sees a system that is loaded leaning east and arriving at the coast ahead of schedule. Now consider what the phrase ENSO neutral actually means, because the country has been told for 2 years that the Pacific was in a neutral state, and a lot of people interpreted that as a kind of permanent calm. It is not calm. ENSO is the El Niño Southern Oscillation, the formal name for the long cycle the Pacific runs through. The cycle has 3 phases. One phase is El Niño, when the central and eastern Pacific run warmer than normal. The opposite phase is La Niña, when those same waters run cooler than normal. The phase in between is neutral. Neutral does not mean the ocean is doing nothing. Neutral means the ocean is between performances. It is the intermission. It is the period when the system is reloading. The Pacific has just finished its intermission. Crossing the plus 0.5 degree threshold is not by itself a catastrophe declaration. NOAA does not ring a bell. The country does not get a press conference. The threshold is a methodological signal, not a disaster signal. It is the agreed-upon line that says the system has officially shifted from one phase of the cycle into another. What happens after the line is crossed is what determines whether 2026 becomes a year people remember. What the country is being shown is the surface. What the country is not being shown is what is underneath it. That plus 0.5 number, the one the headlines are focused on, is the surface reading. What NOAA's instruments are measuring 200 meters below that surface is a completely different story, and that is where Part 2 begins. Part 2, reading the basement of the Pacific, 3 to 4 degrees Celsius. That is how much warmer than normal the water is right now, in a band stretching from the international dateline to the coast of South America, at a depth that no satellite can see. To understand why that matters, picture the equatorial Pacific the way an oceanographer sees it. The surface is a thin film, only a few meters deep, easily warmed by sunlight and easily cooled by wind. Below that surface there is a layer called the thermocline. The thermocline is the boundary where warm surface water meets the colder, denser water of the deep ocean. In the central Pacific, the thermocline normally sits around 100 to 200 meters down. It acts like a lid. The cold, deep water stays below it. The warm, sunlit water stays above it. When the trade winds blow steadily westward across the equatorial Pacific, as they normally do, they push the warm surface water toward Indonesia and the Philippines. They pile it up there. That part of the ocean is called the Western Pacific Warm Pool, and it is the warmest large body of water on Earth. The piling action also tilts the thermocline. In the west, the warm layer gets deep and thick. In the east, near South America, the warm layer gets thin, and cold deep water rises closer to the surface. That is the normal state. Then the trade winds relax. That is what happened at the end of 2025. The wind machine that holds the warm water against Indonesia eased its grip, and when that grip eases, the piled-up warm water in the west does what gravity tells it to do. It begins to slide back east, downhill along the thermocline, in a slow, deep, invisible wave. That wave has a name. Oceanographers call it a downwelling Kelvin wave. It is not a wave you can see at the surface. It is not a wave that breaks on a beach. It is a long, slow pulse of warm water that travels eastward along the thermocline at roughly 2 to 3 meters per second. That sounds slow. It is slow on a human scale. But the Pacific is enormous, and even at that speed, the pulse can cross the entire equatorial basin in a few months. As the warm pulse travels east, it pushes the thermocline downward in front of it. The lid drops. The boundary between warm water and cold water sinks further from the surface. Suddenly, in regions where cold water used to be only 100 meters away from the sky, the warm layer is much thicker. The cold water has been shoved out of the way. And the warm water that was insulated deep down and out of sight now has a direct path upward. NOAA tracks this with an index called the Equatorial Subsurface Temperature Anomaly, averaged across the band from 180 degrees longitude to 100 degrees west longitude, at depths well below the surface layer. That index has been rising for 6 consecutive months, as of NOAA's May 14, 2026 diagnostic discussion. 6 months. Not a single weekly update has reversed it. Inside that band, at depth, the water is running between 3 and 4 degrees Celsius above normal. 3 to 4 degrees does not sound like much when the air conditioner in a living room can change a room by that amount in 20 minutes. In the deep tropical Pacific, 3 to 4 degrees above normal, sustained across an area larger than the continental United States for half a year, is a quantity of heat that is hard to describe without lapsing into hyperbole. It is enough energy to alter atmospheric circulation patterns on the other side of the planet. This is the loading phase. The Kelvin wave is the loading mechanism. The subsurface anomaly is the loaded energy. And the surface reading, the plus 0.5 at Niño 3.4 that the headlines are focused on, is only the first whisper of all that loaded energy beginning to reach the air. Now consider when this began. The subsurface temperature index has been climbing for 6 straight months. That means the loading did not start in May. It did not start in April. It started in December of 2025. While most of the country was finishing the holiday season, the western tropical Pacific was already letting go of its warm pool, and the wave was already on the move. Through January, the wave travelled. Through February, the wave travelled. Through March, the wave travelled. NOAA's weekly diagnostics watched it the entire time. Their internal ENSO teams have been meeting on this signal in every weekly briefing since the new year began. None of those meetings made the national news. None of those weekly updates were broadcast outside the agency. And yet the entire physical preparation for what is now arriving at the surface happened inside those 6 months, in plain view of anyone looking at the right NOAA webpage. The same mechanism has been documented in every major El Niño event since 1982. The wave starts in the west. The thermocline depresses eastward. The subsurface anomaly grows. The surface eventually responds. The pattern is so well established that NOAA scientists can describe its phases in their sleep, and the agency has been refining its detection of this exact loading sequence for more than 40 years. What is different in 2026 is not the mechanism. What is different is the speed and the depth. The subsurface anomaly arrived faster than the central surface response. It arrived with magnitudes at the high end of what NOAA's records show for this stage of a developing event. And the coastal index, Niño 1+2, has already responded at the eastern end of the basin, while the central index is still hovering at the threshold. The basement of the Pacific is full, the lights upstairs have not yet come on, and NOAA's instruments cannot tell you whether the room is going to light up gradually or all at once. But before you can understand what those instruments are actually measuring, there is something you need to know about the ruler they are using, because that ruler changed 4 months ago, and no major news outlet has mentioned it once. So now you know what is moving. But here is the problem. The tool scientists were using to measure how strong it might get was just replaced in February, and that changes every comparison you have ever heard about this. Part 3. The new ruler. Consider a farmer in Fresno County, California in early June. He has farmed almonds, lettuce, and tomatoes for 30 years on land that depends on water from the federal Central Valley Project. He has lived through every El Niño since the early 1980s. He remembers 1997. He remembers 2015. He has a phone in his pocket that he checks the way a retired investor watches a stock ticker. Not because he can change anything, but because the number on the screen determines whether he plants a second crop this year or takes the loss now. He does not know that in February of 2026, NOAA retired the measuring stick that all of those comparisons were built on. For more than 3 decades, the Oceanic Niño Index was the official measuring stick. It was straightforward. NOAA took the 3-month average sea surface temperature in the Niño 3.4 region, and it subtracted from that average a baseline value. The baseline was a 30-year average of temperatures from a fixed historical period. The number that came out the other end was the ONI. Plus 0.5 meant El Niño territory, minus 0.5 meant La Niña territory. Anything in between was neutral, simple, durable, and used in every official discussion of El Niño from the early 1980s until February of 2026. The problem with the ONI was not the math. The math was fine. The problem was the baseline. Because the baseline period was fixed at a specific stretch of decades, and global ocean temperatures kept rising consistently across the decades that followed, every new El Niño was being measured against a yardstick that no longer matched the actual resting state of the Pacific. The Pacific was warmer at rest than it used to be. The baseline did not update to match. So even small upticks in the Niño 3.4 region could push the ONI past the threshold, partly because of an actual ENSO signal, and partly because the background ocean had simply gotten warmer underneath the measurement. NOAA's scientists have been aware of this drift for years. They studied it. They published papers on it. They went back through the historical record and reanalyzed the data with adjusted baselines, and in February of 2026, the agency made the change official. NOAA adopted a new operational tool called the Relative Oceanic Niño Index. The abbreviation is Roni. It looks similar to ONI on paper, it uses similar geography, but it is a different ruler. What the Roni does differently is this. The old index compared the current Niño 3.4 reading to a fixed historical baseline. The new index adjusts for how much the tropical Pacific has already warmed in the background. It subtracts that background trend before doing the comparison. The number that comes out the other end reflects how unusual the current event actually is relative to today's ocean. Not relative to the ocean of 30 years ago. That is a more honest measurement, and it is a different number. NOAA announced the change in a document called NWS Public Information Statement 2605. That document was issued in February of 2026. It went out through the standard agency channels. It was published on the National Weather Service website. It is publicly available, and it received no mainstream news coverage. Let that land. The most consequential methodological change to ENSO monitoring in the agency's history, the kind of change that affects every comparison, every probability calculation, every retrospective analysis of past events, passed without a single major outlet running a story on it. The tool changed. The coverage did not. The reporters who were writing about El Niño in May of 2026 were, in many cases, writing about a number that was not directly comparable to the numbers they had reported in previous events. Some knew, many did not. Here is the consequence that no news outlet has stated. Every comparison being made right now between the 2026 event and the 1997 to 1998 event is technically invalid. The 1997 ONI peak of plus 2.4 degrees Celsius was measured on the old ruler. The 2026 number, when it is reported in Roni terms, is being measured on the new ruler. The two numbers do not mean the same thing. The conversion between them is not a simple subtraction. It is not a fixed offset. The relationship between a 1997 ONI value and what that same event would have read in Roni terms depends on how the tropical Pacific baseline was behaving in that specific year, which is itself a calculation that has not been published in a clean side-by-side form for general use. When a headline says the 2026 El Niño could rival 1997, the headline is comparing apples and a slightly different kind of apple, and the conversion factor between them has not been formally specified. The comparison is not absurd. The structural shape of the two events does resemble each other in the early phase, but the precise quantitative claim that the magnitudes are directly comparable cannot be supported with the index transition that just took place. This is not a minor technical footnote. This is the difference between knowing whether 2026 is comparable to 1997 or not. It also matters for the probabilities. NOAA's May 14, 2026 diagnostic discussion gave an 82% chance that El Niño would emerge by July. That probability is calculated on the new ruler. It is calculated using forecast outputs that have been calibrated to the Roni framework. The models that produce those probabilities have been adjusted accordingly. When you read that 82%, you're reading a number that exists inside the new measurement system. When you read a comparison to a previous event, you're reading a number that was generated inside the old one. This is where institutional change collides with public understanding. NOAA did the right thing by updating the index. The science was sound. The reasoning was published. The transition was documented, but the public was not brought along, and the result is a country reading 2026 numbers through 1997 glasses. Part 4, the 82 and the 37. 82% sounds almost certain. 37% sounds like a long shot. Both of those numbers came from the same NOAA document, issued on the same day, and understanding why they are both true at the same time is the key to reading everything that comes next. The 82% comes from NOAA's May 14, 2026 ENSO diagnostic discussion, and it represents the probability that El Niño conditions will emerge officially by the time July ends. The 96% in the same document represents the probability that El Niño will still be active through the winter of 2026 to 2027. Those numbers are the headline numbers. They are the ones that travelled. They are the ones that justify the words almost certain in any honest sentence written about this event. But the same document contains a second set of numbers. Those numbers describe the probability of how strong the event becomes if it does emerge. NOAA breaks this down into 4 strength categories. There is weak, there is moderate, there is strong, and there is very strong, sometimes called Super El Niño territory. Each category corresponds to a range of ONI or Roni values that the event might peak at during its mature phase. In the May 14th diagnostic, no single one of those 4 strength categories exceeded a 37% probability. To understand what that means, picture how NOAA builds these forecasts in the first place. The agency does not run one model, it runs many. There is a collection of dynamical models, which are full physics simulations of the ocean and atmosphere, run on supercomputers that try to predict what the climate system will do next based on its current state. There are statistical models, which look at historical analogues and patterns and project forward based on what similar setups have done in the past. NOAA and its partners, including the International Research Institute for Climate and Society at Columbia University, assemble all of those model outputs into a single picture called the model plume. At the Environmental Modeling Center in College Park, Maryland, Those simulations run on a machine that completes more calculations per second than every human being alive could perform in a year. The output arrives as a graphic, dozens of forecast lines, branching and diverging, each one a different version of the next 6 months. A forecaster sits down with that graphic every month and has to reduce it to a single probability statement. The plume is a visual showing the spread of where every model thinks the ONI is going to be in each upcoming month. The probabilities for each strength category come from looking at the spread of that plume and asking, of all these forecast lines, how many of them land in each strength bracket at the projected peak. If half the models land in moderate, moderate gets close to 50%. If the lines are spread evenly across weak, moderate and strong, the probabilities are smaller for each category because the models disagree on which one is most likely. That is what is happening right now. The models do not disagree on whether El Niño is coming. Their agreement on that question is what produced the 82% probability. Where they split apart is the strength question. On that question, the spread of model outputs is wide enough to span from a minor event to a record one. Reading the structure of the distribution from the framing NOAA provided, the combined weight on weak to moderate outcomes exceeds the combined weight on strong to very strong outcomes, with a 37% ceiling applying to any individual strength category. NOAA did not publish the combined category percentages directly, but the shape of the distribution is clear. Most of the probability mass sits below the strong threshold. The most likely single outcome is moderate. The second most likely is either weak or strong, depending on how the next few weeks unfold. Very strong is possible, but is the least likely of the 4 categories. What that 37% ceiling actually means in practice is that NOAA is essentially saying the ocean has loaded enough energy to produce anything from a weak event to a record breaker, and the instrument data cannot yet tell the difference. The signal in the subsurface is strong enough to make El Niño nearly certain. It is not yet strong enough to tell you which El Niño. That is the part of the message that gets lost in the headlines, because 37% when written next to phrases like strong El Niño reads as a warning, and it is a warning. But it is not a forecast of a strong El Niño. It is a forecast that strong El Niño is one of 3 plausible outcomes, and the other 2 are still more likely combined. For the probability distribution to shift between now and the June 11th update, specific things would have to happen in the data. The model plume would have to converge. Right now, the dynamical models and the statistical models are not pointing at the same number for the projected peak. Some are projecting peaks around plus 1.2, others are projecting peaks above plus 2. As more observational data comes in through May, those forecasts get reinitialized with the latest state of the ocean and atmosphere. If the May data shows stronger surface warming, stronger atmospheric coupling signals, or a deeper Kelvin wave structure, the models tighten their estimates and shift the probability distribution. A tightening that pulls the distribution toward the high end would show up as the strong category climbing above 40%. A tightening that pulls it toward the low end would show up as the weak category gaining ground, and the strong category receding. Either move would be significant. Neither move is guaranteed. The June 11 update could also report that the distribution is essentially unchanged, which would itself be informative. It would tell us that the data has not yet broken the symmetry of possible outcomes. There is a temptation, watching this kind of probability discussion unfold, to ask which number is the right one to remember. The honest answer is that they all are. The 82% tells you the event is almost certainly coming. The 37% tells you the strength of it is genuinely uncertain. The 96% tells you the event, once arrived, persists through next winter. None of those numbers contradicts the others. They are 3 different questions, each with its own answer, and reading any one of them in isolation produces a distorted picture. The mechanism that determines which El Niño this becomes, the one that separates a moderate correction from a 1997 scale event, has a name, and it happens in the atmosphere, not the ocean. That is Part 5. Part 5, the summer that decides everything. The ocean has done its part. For 6 months, it has been loading heat into the subsurface layer of the equatorial Pacific. Now it is waiting for the atmosphere to respond, and whether or not the atmosphere responds in the next 60 days is the only question that matters. To see why, consider how the normal Pacific works. The atmosphere over the equatorial Pacific runs a giant east-west loop called the Walker Circulation, named for the British scientist Sir Gilbert Walker, who first described it in the early 20th century. air rises over the warm western Pacific warm pool near Indonesia and the Philippines. It flows eastward across the upper troposphere. It sinks over the cool eastern Pacific near South America, and it returns westward at the surface as the trade winds, blowing along the equator from the coast of Peru back toward Indonesia. The whole loop is driven by one thing: the temperature difference between the warm western pool and the cool eastern Pacific. That gradient is what makes the air rise in the west and sink in the east. The gradient is what keeps the trade winds blowing westward. The gradient is the engine. When El Niño warming reaches the surface of the central and eastern Pacific in significant magnitude, the gradient weakens. The eastern side warms up. The temperature difference between east and west collapses, and when that gradient collapses, the entire Walker loop weakens with it. The trade winds weaken. That is the critical step, because the trade winds were the wind machine holding warm water against Indonesia in the first place. When the trade winds weaken, more warm water spreads east. More warm water at the surface in the east further reduces the gradient. The Walker circulation weakens more. The trade winds weaken more. It is a feedback loop. Each step amplifies the next. Scientists call it the Bjerknes feedback, named after Jacob Bjerknes, the Norwegian-American meteorologist who described it in the late 1960s. That feedback loop is what transforms a subsurface heat anomaly into a full El Niño event. Without the atmospheric response, the warm water at the surface eventually radiates its heat back into the atmosphere and the system relaxes. The Kelvin wave dissipates. The thermocline returns to its normal tilt. The event peters out as a brief, modest surface warming with limited downstream consequences. That has happened before, in years when the ocean loaded heat and the atmosphere did not respond. Forecasters sometimes call it a failed El Niño. The ocean was ready. The sky did not cooperate. But when the atmosphere does respond, when the Walker circulation weakens and the trade winds collapse, and the Bjerknes feedback locks in, the system accelerates. The Peakoni value climbs further. The teleconnection patterns that route impacts to North America strengthen. The event becomes the kind of El Niño the country remembers for decades. This process has a name. NOAA scientists call it ocean-atmosphere coupling. And in their May 14, 2026 diagnostic discussion, they made an explicit statement about it. The exact wording in the document was, in plain summary, that the strongest El Niño events in the historical record are characterized by significant ocean-atmosphere coupling through the summer, and that it remains to be seen whether this occurs in 2026. That phrase, "it remains to be seen," is doing a lot of work. NOAA scientists are watching a system that has all the physical preconditions for a major event. They are watching it in real time, every week, with the best instrument network ever deployed for this purpose. And they do not yet know which way it breaks. The Kelvin wave is in the right place, the subsurface anomaly is the right size, the coastal index is responding the way it did in 1997. But the trade winds have not yet collapsed in the Central Pacific. The Walker circulation has not yet weakened decisively. The atmosphere has not yet signaled that it is going to engage with the ocean signal. When the agency says it remains to be seen, that is not casual hedging. That is the precise language of scientists who are staring at two diverging futures and cannot yet tell which branch the data is on. There are specific atmospheric indicators that signal coupling beginning to engage. The first one is the Southern Oscillation Index. This SOI measures the difference in atmospheric pressure between the city of Tahiti in the central South Pacific and the city of Darwin on the northern coast of Australia. In a normal Pacific, the pressure is higher at Tahiti and lower at Darwin, because rising air over the warm pool near Darwin produces lower surface pressure there. The pressure difference between the two cities is one of the oldest measurements in modern meteorology. It goes back more than a century. When El Niño coupling engages, that pressure difference collapses and then reverses. The pressure at Darwin rises, the pressure at Tahiti falls. The SOI goes negative, sometimes strongly negative. A sustained negative SOI is one of the clearest atmospheric signatures that the Walker circulation has weakened and the trade winds have lost their grip. The second indicator is the pattern of low-level wind anomalies over the central equatorial Pacific. Forecasters look at whether the easterly trade winds in that band have weakened, stopped, or reversed into westerlies. When westerly wind anomalies appear in the central Pacific, that is the trade wind machine breaking down in real time. That is the loop closing. Both of those indicators are watched in every NOAA diagnostic discussion. Both of them, in the May 14th document, were not yet showing decisive coupling signatures. The SOI was hovering, not yet plunging. The low-level wind anomalies were present but not dominant. The atmosphere was not yet engaged. The next 60 days are the window in which it would engage if it is going to. The seasonal climatology favours coupling onset between late spring and midsummer in events that are going to become strong. If by August the atmosphere has not engaged, the event most likely tracks as a weak to moderate El Niño with modest downstream impacts. If by August the atmosphere has engaged, the event has the structure of a major one. The stakes of that 60-day window are not abstract. They are the difference between a winter that brings some relief to California reservoirs and a winter that brings catastrophic flooding. They are the difference between a slightly quieter Atlantic hurricane season and an unusually quiet one. They are the difference between a manageable wildfire year in the Pacific Northwest and a punishing one. The atmospheric response in May, June and July of 2026 determines which version of the next 12 months the country is about to live through. The last time the Pacific loaded this much subsurface heat and then achieved full ocean-atmosphere coupling through the summer, the only peaked at plus 2.4 degrees Celsius. That was 1997, and what happened in 1997 is exactly where Part 6 goes. Part 6, 1997, The Ghost in the Data. In the spring of 1997, NOAA's instruments were reading almost exactly what they are reading right now. A subsurface temperature anomaly running 3 to 4 degrees above normal, a Niño 1+2 reading already elevated above the Central Pacific, and a probability discussion that used the word uncertainty in the same sentence as the word significant. Nobody on the operational forecast desks that spring knew they were about to live through the strongest El Niño in the modern instrumental record at that time. They knew something was coming. They did not yet know what. The structural setup in 1997 mirrored what is being seen in 2026 with eerie precision. The Kelvin wave initiated in the Western Pacific in late 1996 and early 1997. The trade winds in the Western Basin relaxed. The thermocline tilted eastward. The subsurface anomaly grew through the first months of the year. The Niño 1+2 region near the coast of South America warmed first and warmed fastest. The Central Pacific responded more slowly. By March, the ONI had crossed the plus 0.5 threshold. The event had officially begun. Then, between May and August of 1997, something happened that forecasters did not see coming with the speed at which it actually arrived. The atmosphere coupled. The Walker circulation weakened. The trade winds in the Central Pacific collapsed and reversed into westerlies. The Bjerknes feedback locked in. The ONI climbed from plus 0.8 in spring to plus 1.7 by July, and it kept climbing. By October, November, and December of 1997, the ONI was reading plus 2.4 degrees Celsius. That was the highest recorded value in the instrumental record up to that date. At the time, the 1997 to 1998 El Niño held the record as the largest event the modern instrumental network had ever captured. What it did to the world once that peak was reached is documented across multiple damage assessments. The death toll, when totaled across all regions affected by the cascading impacts, has been estimated at roughly 23,000 people globally, based on climate impact assessments compiled after the event. The direct economic damages in California alone have been placed at more than $550 million from flooding, mudslides, and storm damage during the winter of 1997 to 1998. Figures drawn from post-event surveys conducted by state and federal agencies. Highways were closed. Hillsides came down on homes in coastal counties. Atmospheric rivers, one after another, slammed into the western coast for weeks at a time. In coastal Peru, the impacts were of a different magnitude entirely. The warm coastal water that had appeared off Ecuador and northern Peru collapsed the fishing economy. The anchoveta, the small forage fish that the entire Peruvian fishing industry depends on, migrated south in search of cooler water. The catch crashed. Rivers that had been low for years suddenly received torrential rainfall and flooded their banks. Coastal infrastructure, fishing fleets, processing plants, and small towns were destroyed. Thousands died in the flooding. The damage to fishing infrastructure took years to rebuild. On the other side of the Pacific, Indonesia experienced the most severe drought it had recorded in the 20th century. Rainfall in the Western Pacific warm pool region collapses during a strong El Niño because the rising air that normally produces convection there has shifted east, following the warmer water. Without that rising air, the convective rainfall that supports Indonesian agriculture and forest moisture simply does not arrive. Fires set to clear land, and others that ignited naturally, found tinder-dry forests waiting for them, and they burned across Sumatra and Borneo for months. The smoke from those fires blanketed Southeast Asia. Air quality in cities thousands of miles from the fire sources collapsed. Hospitals reported surges in respiratory illness. Visibility at airports across Malaysia, Singapore, and parts of Thailand dropped so low that flights were suspended for weeks at a time. In sub-Saharan Africa, the teleconnection patterns rerouted rainfall away from regions that depended on it. Drought conditions worsened across parts of southern Africa. Crop failures spread. International relief agencies issued famine warnings across the region. Deaths from food insecurity in that period contributed to the global 23,000 figure, and they were the consequence of a temperature anomaly in a stretch of ocean none of those farmers had ever seen. The 1997 to 1998 El Niño remade national budgets, displaced communities, and reshaped the way international agencies coordinated disaster response. It also reshaped the way climate scientists communicated uncertainty. Because the rapid intensification between May and August of 1997 had surprised the forecasters. The models had projected significant warming. They had not projected how fast it would happen. The model ensemble that spring carried structural uncertainty about the speed at which coupling would lock in, and once coupling did lock in, the system accelerated faster than the monthly update cycle was capturing. By the time the August update came out, the situation on the ground had already moved beyond what the July update had projected. The models knew something was coming. They did not know it would move that fast. That same structural uncertainty exists in 2026. The models in the May 14th diagnostic acknowledged it implicitly when they put no single strength category above 37%. The reason the distribution is wide is that the models cannot yet tell, with their current observational inputs, how aggressively the atmosphere will couple if and when it does. If coupling locks in quickly, the event accelerates. If coupling drags, the event remains moderate. The window between those two outcomes is small in time. It can be the difference between a few weeks of atmospheric behavior in late spring and early summer. The story of 1997 is not just a story about damage. It is a story about a moment in the months between May and August, when the ocean had already done what it was going to do, and the atmosphere was deciding whether to amplify or absorb the signal. That moment is the moment 2026 is currently in. The damage of 1997 to 1998 was the consequence of the atmospheric decision. The damage was not a separate event. It was the downstream signature of an atmospheric coupling that took less than 90 days to lock in. What that meant for the people who lived through it deserves more than a line in a damage report. Consider a fishing family in Chimbote, on the north-central coast of Peru. In 1997, Chimbote was the largest fishing port in the world by tonnage. The town had grown up around the anchoveta industry. The boats left at 4 a.m. and returned in the afternoon with their holds full. The processing plants ran in shifts day and night. Generations of families had worked the same waters. Picture a grandfather in that town watching the sea temperature climb through the summer of 1997, not yet knowing what was coming. He had fished the same waters for 40 years. He had seen lean seasons. He had seen good seasons. He had seen the ocean change in small ways and right itself. The warming that summer felt different to him, but he could not have named why. The boats kept going out. The catch declined gradually. Then, in the last months of 1997, the decline accelerated. By January of 1998, the anchoveta had migrated south, far south, into colder water that was now hundreds of miles from where his town's boats could reach. The nets came back up empty. The processing plants slowed, then stopped. The grandfather, who had never once in 40 years come home with nothing, came home with nothing for the first time in his life, and then again, and then again. He was not in the news. His town was in the news, but he, as a person, was not. He was one of tens of thousands of people whose work, whose income, whose role in the household vanished because of a temperature pattern in a stretch of ocean that none of them could see. Part 7. The 4 American Fault Lines. The 4 things El Niño is going to touch first in the United States are already under stress, and in 3 of the 4 cases that stress began before El Niño arrived. The first is California's Central Valley. The Central Valley produces more than 1/3 of the vegetables grown in the United States, and more than 2/3 of the fruits and nuts. It is the most productive agricultural region in North America. It runs 450 miles from the Cascade foothills near Redding down to the Tehachapi Mountains near Bakersfield, a corridor of farmland that feeds people in every state. And it entered the spring of 2026 with snowpack at or near record lows in the Sierra Nevada mountains, which supply the bulk of its irrigation water through the spring and summer melt season. The 2026 growing season will not benefit from El Niño's winter precipitation signal. This is a point that gets confused often, because people hear El Niño and think wet, and then they assume the rain arrives in time to help the current crop. It does not. El Niño's above normal precipitation signal for California applies to winter 2026 to 2027. That is 6 months from now. The fields that are being planted right now, the orchards that are setting fruit right now, the cattle that need feed right now, will not see any rain that El Niño delivers until next winter. Growers face the full cost of drought now before any relief arrives. Some will pull out almond orchards entirely rather than pay for the water to keep them alive through this summer. Some will fallow fields they have farmed for decades. The federal water allocations from the Central Valley Project are already reduced. The state water deliveries are already reduced, and the price of the water that is available on the open market has climbed to levels that strain even the largest operations. The second fault line is the Pacific Northwest, specifically the forests of Washington and Oregon. The governor of Washington declared a statewide drought emergency in the spring of 2026. The proclamation cited soil moisture levels among the lowest the state had ever recorded for the early growing season, depleted reservoirs, and snowpack deficits across the Cascades. The Pacific Northwest is entering its fire season in conditions that were already worrying without El Niño in the picture. What El Niño does to the Pacific Northwest is push the winter and early spring conditions warmer and drier than they would otherwise be. The teleconnection pattern that develops during a strong El Niño tends to suppress winter storms over the northern tier of the western United States, including Washington and Oregon, while enhancing them over California and the Southwest. That means the recovery the Northwest needs, in the form of late-season precipitation and a robust snowpack rebuild next winter, may be reduced by El Niño's directional push. The drought that exists now is being met by an atmospheric pattern that, historically, makes droughts worse in that region, not better. The combination of existing drought and El Niño's directional push creates compounding risk through the next 12 to 18 months. The third fault line is the Gulf Coast and the Southeast. This is the one impact where El Niño's arrival is, on balance, good news for American lives. El Niño increases vertical wind shear over the tropical Atlantic. Vertical wind shear is the difference in wind speed and direction between the surface and the upper atmosphere. When wind shear is high, developing hurricanes have a harder time organizing. The thunderstorm towers that hurricanes need to maintain their structure get torn apart by the changing winds at different altitudes. The storms either fail to form or weaken before they reach landfall. The historical record on this is fairly consistent. Strong El Niño years tend to suppress Atlantic hurricane activity by roughly 25 to 30% compared to neutral years. The number of named storms drops. The number of hurricanes drops. The number of major hurricanes drops more sharply still. For the Gulf Coast from Texas to Florida, and the Atlantic Southeast from Florida up through the Carolinas, a strong El Niño year is on average a year with fewer storm strikes and less destruction. The irony of this is real, and it deserves to be named directly. The same ocean warming that threatens California's agriculture and the Pacific Northwest's forests is simultaneously the mechanism that reduces the number of storms heading toward the Gulf Coast. El Niño is not uniformly dangerous. For some American communities, a stronger El Niño is better news than a weaker one. That asymmetry is real, and it is not how the story is being told. The headlines that frame this event as a disaster in the making for the country as a whole are flattening a much more complicated picture. There are coastal residents in Louisiana, Mississippi, Alabama, and the Florida Panhandle for whom a strong El Niño literally improves the odds of getting through hurricane season without their home being destroyed. NOAA is explicit that the suppression is probabilistic, not guaranteed, and that a weaker El Niño produces a weaker suppression effect. But the directionality of the impact for those communities is favourable. The fourth fault line is the Colorado River Basin, and specifically Lake Powell. Lake Powell is the second largest reservoir in the United States by volume when full. It sits behind Glen Canyon Dam on the Utah-Arizona border. 40 million Americans across 7 states depend on its water: Phoenix, Las Vegas, Los Angeles, San Diego, Denver, Albuquerque, and dozens of smaller communities that most people in those cities have never thought about once, even as they turn on the tap. As of the spring of 2026, Lake Powell sat at roughly 24% of capacity. That is not an isolated low point. It is the latest data point in a long, slow decline that has been running for more than 2 decades. The reservoir has not been full in living memory for most younger Americans. The bathtub ring of mineral deposits on the canyon walls, marking previous shoreline levels, is now visible from the air at a height that astonishes anyone who saw the lake in the 1990s. El Niño's above normal precipitation signal for the southwest in winter 2026 to 2027 is the first realistic reservoir recovery pathway for Lake Powell in years. The Colorado River's headwaters depend on snowpack in the central and southern Rocky Mountains, and the El Niño teleconnection pattern tends to enhance precipitation in that region. A wet winter in the Colorado headwaters means a strong spring runoff, which means a meaningful refill of Lake Powell and the reservoirs downstream of it. But that recovery depends on a strong enough event. A weak El Niño produces a weak teleconnection signal. A weak teleconnection signal produces near normal precipitation, which is not enough to reverse a deficit that has been accumulating for 20 years. A strong El Niño produces a much more vigorous precipitation response, and in the historical record, the strongest El Niños have produced the largest single-year Colorado Basin recoveries. Whether 2026 delivers the strong version or the weak version is exactly the question parts 1 through 6 have been building toward. The reservoir recovery is not guaranteed. It is contingent on the same atmospheric coupling decision that determines every other impact. All 4 of those scenarios, the drought, the fires, the hurricanes, the reservoir, play out differently depending on one thing: how strong the signal that reaches the atmosphere actually is, and that depends on a process that Part 8 explains from the ground up. Part 8, when the ocean talks to the sky. There is a reason that forecasters do not just say more rain for California, they say potentially catastrophic flooding. The difference between a weak El Niño and a strong one is not a bigger number. It is a completely different atmospheric machine. To see why, return to the Walker circulation in its normal configuration. East-west loop. Air rises over the warm western Pacific. Air sinks over the cool eastern Pacific. Trade winds blow westward at the surface. The whole loop is driven by the temperature gradient between west and east, and the strength of that gradient determines how vigorous the whole circulation is. When El Niño warming reaches the surface in significant magnitude, the gradient weakens. The rising air shifts east, following the warm water toward the central Pacific. The sinking branch of the circulation moves with it. The whole loop reorganizes, the atmospheric center of mass shifts thousands of miles east, and that reorganization sends ripples outward. Forecasters call those ripples teleconnections. The word literally means connections at a distance. A teleconnection is a pattern of correlated atmospheric variability that links one region of the planet to another through the medium of the global atmospheric circulation. When the equatorial Pacific shifts state, the consequences do not stay in the equatorial Pacific. They radiate outward, through the jet streams, through the polar vortex, through the storm tracks that move heat and moisture around the globe. The specific teleconnection that matters most for the United States is called the Pacific North American Pattern, or the PNA. It is a wave train, a sequence of high and low pressure centers that propagates northeastward from the central Pacific across North America. When El Niño warming activates the PNA in its positive phase, the pattern produces a characteristic configuration. A deepened low-pressure center settles into the Gulf of Alaska. A ridge of high pressure builds over western Canada. A trough deepens over the southeastern United States. And the jet stream, the high-altitude river of fast air that steers storms across the country, drops south, dipping down over California and the southwest before curving back north toward the southeast. That shift in the jet stream position is the key. The jet stream is the steering current for winter storms. When it shifts south over California, more storms reach California. When it shifts further south, storms that would have died over the open Pacific instead drive straight into the west coast. When the pattern locks in for weeks at a time, the same storm track recycles, delivering one storm after another to the same regions. What is critical to understand is that the teleconnection response does not scale proportionally with the ONI value. This is the nonlinearity that catches forecasters and the public off guard year after year. At only plus 0.8 degrees Celsius, the teleconnection signal is detectable but weak. The jet stream shifts slightly. California sees somewhat above average precipitation, The southwest gets a modest boost, nothing dramatic, nothing historic. At only plus 1.5 degrees Celsius, the teleconnection signal is significantly amplified. The jet stream shift becomes more decisive. The Gulf of Alaska low deepens. California sees substantially above average precipitation. The southwest sees a strong signal. Storms that would not have reached land instead reach land. Snowpack rebuilds aggressively. Reservoirs see meaningful refill. At only plus 2.0 degrees Celsius or above, the signal can lock the jet stream into an anomalous southward position for an entire season. The pattern stops varying, it stops oscillating, it settles into a regime that holds for weeks or months. And that is not a 50% increase in California rainfall, it can be a 200% of normal year. The difference between moderate and strong is not linear, it is a phase shift. This is what turned the 1997 to 1998 winter into a flood disaster in California. It was not one big storm, it was the same storm track recycled repeatedly for 3 months. Each storm delivered as much moisture as a slow-moving tropical system. Atmospheric rivers, which are narrow corridors of concentrated water vapor flowing from the tropical Pacific toward the west coast, formed one after another. Each one dumped rainfall measured in inches per hour over already saturated ground. Each one filled streams that were already at capacity. The state was not hit by a single hurricane. It was hit by a recurring weather pattern that the locked jet stream kept feeding new storms into. The cumulative damage came from the repetition, not the intensity of any single storm. The 2015 to 2016 winter produced a different version of this same phenomenon, which is the calibration point Part 9 addresses. But the underlying mechanism is the same, the jet stream's position and persistence, set by the teleconnection response to the equatorial Pacific warming, determines whether a season's storm budget arrives in measured installments or as a continuous weeks-long bombardment. For the Pacific Northwest, the same teleconnection that boosts California's storms suppresses theirs. The deepened low over the Gulf of Alaska tends to steer storms south of Washington and Oregon, leaving those states drier than they would be in a neutral year. The mountains that should be accumulating snow through the winter accumulate less. The forests that depend on that snowpack to keep soil moisture high through the summer enter the dry season with deficits. The wildfire risk in subsequent years compounds. For the Atlantic Basin, the equatorial warming routes through a different mechanism. The shift in tropical convection from the western Pacific to the central Pacific changes the upper atmospheric winds across Central America and the Caribbean. Those altered winds increase wind shear over the western Atlantic, the Gulf of Mexico, and the Caribbean Sea. High wind shear is hostile to tropical cyclone development. Storms that would have formed do not form. Storms that do form weaken faster than they otherwise would. For the southern tier of the United States, including the Gulf states and Florida, the deepened trough over the southeast tends to bring cooler, wetter winters, with more frequent storm systems crossing from west to east. The Mississippi River Basin can see enhanced precipitation. Texas and the Gulf Coast can see flooding events. Each of these regional impacts depends on the teleconnection signal being strong enough to organize the atmosphere into a stable pattern. A weak signal produces ambiguous effects. A moderate signal produces detectable effects. A strong signal produces dominant effects. A very strong signal produces a fundamentally altered atmospheric regime for the duration of the event's mature phase. The 2015 to 2016 El Niño peaked at an ONI value that at the time made it the strongest event in the modern instrumental record, measured at roughly plus 2.6 degrees Celsius according to subsequent NOAA tabulations, though the Roni transition discussed in Part 3 affects how that comparison should be understood. California forecasters warned it would be the worst flood season in decades. They were not entirely wrong, but they were also not entirely right, and what happened in 2015 and why is exactly the calibration Part 9 provides. Part 9, 2015 and what it didn't do. The strongest El Niño ever recorded, stronger than 1997 by 0.2 of a degree, under-delivered on its worst-case forecast for California. That result changes how the 2026 probability numbers should be read. The 2015 to 2016 El Niño reached its peak during the late fall and early winter season of 2015 to 2016. That value made it, by the official scoreboard, the strongest El Niño in the instrumental record at that time, edging out the 1997 to 1998 peak of plus 2.4. Going into the winter of 2015 to 2016, forecasters projected a very wet season for California, especially for the central and southern parts of the state, and they projected significant drought relief for the southwest. The state had been in a punishing multi-year drought. Reservoirs were low, communities had been on water restrictions for years. The El Niño forecast was something the state had been hoping for since at least 2012. What happened was not what people remember it as. California did receive above-normal precipitation in southern regions during the winter of 2015 to 2016. Los Angeles got rain, San Diego got rain, the Southern Sierra got snow, but the Northern Sierra Nevada, which is the primary source of California's water supply, through the major federal and state water projects, underperformed. The teleconnection pattern delivered precipitation differently than the models had expected. Storms tracked through the state in a pattern that favored the south more than the north. The snowpack that the state most needed in the high northern Sierra did not rebuild to the level that the magnitude of the El Niño had suggested it would. The drought did not end in 2015 to 2016, it continued. A small recovery was made, but the deep deficit accumulated through the preceding years was largely intact. The state had to wait until the winter of 2016 to 2017, which brought a sequence of atmospheric rivers under different atmospheric conditions, to see the kind of broad-based water year that finally moved the reservoirs back toward normal. The forecasting community took this result seriously. The post-event analysis was extensive. The conclusion, in plain terms, was that peak-only value alone does not determine downstream impact. The teleconnection response depends on more than just how warm the Central Pacific is. It depends on where within the Niño regions the warming is concentrated. It depends on the background state of the Pacific Decadal Oscillation, a much longer-running mode of Pacific variability that influences how the atmosphere responds to equatorial perturbations. And it depends on the position of the warming anomaly relative to the atmospheric heating maximum, which is the specific patch of Central Pacific where convective rainfall becomes most intense during an El Niño event. In 2015, the warming had a slightly different spatial pattern than 1997. The Central Pacific warmed strongly, but the heating maximum sat in a position that nudged the teleconnection response slightly northward. That nudge moved the jet stream's center of action away from the optimal latitude for delivering storms into the northern Sierra. The result was that the southern regions of the state received a wetter season than normal, but the regions that mattered most for the state's water infrastructure did not. The 2015 peak number was right. The models predicted correctly that the Oni would reach plus 2.6 degrees Celsius. The downstream prediction was partially wrong. The spatial distribution of the impacts diverged from what the headline forecast had implied. NOAA learned from that discrepancy. The agency's research divisions, working with academic partners, spent years analysing why the teleconnection response had been less favourable for the Northern Sierra than the magnitude of the event would have predicted. Part of what that analysis produced is the Roni transition itself. By isolating the ENSO variability from the background warming, the Roni gives a cleaner signal of what is genuinely different about each event, which makes it easier to compare events with different background states. The improvement is methodological. It does not eliminate the underlying uncertainty. It addresses one source of comparison error and leaves others in place. What it teaches about 2026 is direct. The peak number that NOAA eventually reports for the 2026 to 2027 event, whether it is reported as Oni or Roni, matters. It matters a lot. But the character of the event, where the warmest water sits within the Niño regions, how the atmospheric heating maximum organizes, what the Pacific Decadal Oscillation is doing in the background, all of that determines how the teleconnection lands on specific regions. Two events with the same peak number can produce noticeably different impact patterns. Two events with different peak numbers can produce surprisingly similar regional outcomes if their spatial patterns happen to align. Consider a water manager at the Metropolitan Water District of Southern California in the fall of 2015. The Metropolitan Water District is the largest water wholesaler in the United States. It supplies water to 19 million people across 6 counties in Southern California. Its planning horizon is decades. Its reservoirs and aqueducts represent some of the largest pieces of public water infrastructure ever built. In the fall of 2015, the manager was sitting in planning meetings at the Metropolitan Water District's headquarters in downtown Los Angeles, looking at the forecast for the strongest El Niño ever recorded, and making decisions about how to operate Diamond Valley Lake and the district's other storage reservoirs through the coming winter. One of the standard procedures during a forecast wet year is to release water from reservoirs in advance, to create empty storage capacity for the flood season. Holding too much water risks the reservoir overtopping when the storms arrive. Releasing too much risks giving away water you will not be able to replace if the storms underperform. The manager that fall was working from the official forecast. The forecast said the Northern Sierra would deliver a major snowpack and a major runoff. The planning assumptions allocated storage space in anticipation of that runoff. Water was released ahead of the season. Reservoir levels were brought down. The Northern Sierra got less than projected. The runoff was modest. The storage space that had been freed for floodwaters that did not fully arrive was space that could have held water for the following dry year. The decisions that had been made in good faith based on the best forecast available did not pay off the way the forecast had suggested they would. No one was negligent. No one had ignored the data. The data had simply not captured the full pattern that ended up unfolding. The water managers of California today, planning for the winter of 2026 to 2027, are working from forecasts that have been improved since 2015. The models are better. The methodology is more honest about the uncertainty. The Roni transition addresses one of the comparison errors that affected the 2015 forecast cycle. But the fundamental pattern uncertainty has not been eliminated. The next event's spatial pattern is still partly unknown until the event develops. The same questions that surprised the 2015 forecast can surprise the 2026 one. The water manager made the right call with the wrong forecast. That distinction, right process, wrong outcome, is the one that matters most for understanding what June 11 will and will not deliver. Part 10. What 6 days means. June 11th, 2026. 6 days from now. That is when NOAA publishes the document that answers the question this entire video has been building toward, and tonight this part is going to tell you exactly how to read it. The document is called the ENSO Diagnostic Discussion. It is issued by NOAA's Climate Prediction Center, which operates as part of the National Weather Service. The discussion is published on the second Thursday of each month. It runs roughly 4 to 6 pages of dense scientific text. It includes the official current ENSO state designation, a description of the most recent observational data, a discussion of the model forecasts, and a probability distribution for the coming months and seasons. The June 11th update will draw on the full May 2026 observational dataset. That includes the monthly average sea surface temperatures across all 4 Niño regions, the subsurface temperature anomaly profile from the TAO buoy array, and from Argo floats, the Southern Oscillation Index value for the month, the low-level wind anomaly data from the Central Pacific, and the outgoing long-wave radiation patterns that indicate where deep convection is occurring in the tropics. All of those inputs will have been compiled, quality-checked, and processed by the time the discussion is issued. What to look for when you open the document comes down to a small number of specific data points. There are 3 numbers worth watching closely. The first is the updated probability distribution across the strength categories. In the May 14th document, no single category exceeded 37%, with the most likely outcome being moderate. If the June 11th update shows the strong category rising above 40%, the forecast ensemble has shifted toward the upper end. That would be a meaningful change. It would tell you that the May observational data pushed the models in the direction of a stronger event. Conversely, if the weak category gains probability at the expense of moderate, the event may be peaking earlier and weaker than projected, which would also be a meaningful change in the other direction. The shape of the distribution, not just the headline emergence probability, is the part to read carefully. The second number is the Southern Oscillation Index value for May. If the SOI has moved significantly negative by the time the June 11 document is published, atmospheric coupling is beginning to engage. A sustained negative SOI is one of the clearest atmospheric signatures that the Walker circulation is weakening. The document will report the monthly average. It may also discuss the trend during May, whether the index was negative throughout the month or only at the end. Both pieces of information matter. A late May plunge into negative territory is more meaningful than an early month dip that recovered. The third number is the equatorial subsurface temperature anomaly for May. The index has been rising for 6 consecutive months. A 7th consecutive monthly increase would confirm that the Kelvin wave structure is still building. A flattening would indicate the loading phase may be peaking. A slight decline would not necessarily mean the event is failing, because the loaded heat can move toward the surface as it spreads east, but it would change the interpretation of where the energy currently sits in the system. There are other numbers in the document worth noticing. The Niño 3.4 monthly sea surface temperature anomaly will be reported. The Niño 1+2 value will be reported. The outgoing long-wave radiation patterns will be discussed in narrative form, indicating where the convective rainfall maxima are sitting. The model plume figure, usually included as one of the diagnostic graphics, will show the updated spread of forecast outcomes. Each of those data points adds context. The document is freely available to anyone with an internet connection. The URL is cpc.ncp.noaa.gov/product/analysis_monitoring/enso_disc.html. That last word is SHTML run together, the standard web file extension. That address has been stable for years. The document is posted there in the late morning Eastern Time on the second Thursday of each month, which is what makes the June 11 date specific. Here is the part that needs saying clearly. The June 11 update cannot resolve the question entirely. Even if the strong category rises to 45% in the new probability distribution, even if the SOI has moved strongly negative, even if the subsurface anomaly has continued to build, the distribution will still show meaningful weight on moderate and weak outcomes. The update will narrow the range of plausible futures. It will not close that range. The final resolution of whether 2026 becomes a 1997 scale event will not be known until the ONI or Roni reading for the July to September season is available, which means the uncertainty window extends through October. The system needs another 3 to 4 months to fully reveal which branch it is on. NOAA will publish discussions every month through that window. Each one will narrow the range a little further. None of them will settle the question definitively until the event is well into its mature phase. June 11th is not the answer. It is the first reduction in the uncertainty range. It is the first formal update that incorporates the full May observational picture, and it will tell us whether the trajectory has accelerated, decelerated, or held its course. The agency will use careful language. They will say the system has continued to evolve toward El Niño conditions, or that the probability has increased slightly, or that the strength distribution has shifted. They will not say catastrophe. They will not say crisis. They will say what the data shows, and they will hedge where the data is uncertain. That is what reading the document directly gives you that the news coverage will not. You will see the hedges. You will see the uncertainty acknowledged. You will see the probability distribution and not just the headline number. You will be reading what the scientists actually wrote, in the form they actually wrote it, with the qualifications they actually included. It is worth saying that NOAA's documents are written for a technical audience and use vocabulary that takes some practice to read fluently. But the structure is consistent month to month. Once you have read 2 or 3 of them, the pattern becomes familiar. You learn where the strength probabilities are reported. You learn where the SOI value appears. You learn where the model plume is described. The 4th or 5th document is much easier to read than the first, so in 6 days we get better information. But some of what the news is already saying about this event is not better information. It is noise dressed up as data. And part 11 is where we go through exactly what the headlines got wrong, and exactly what the actual NOAA document says. Part 11, the headlines got it half right. Most news stories about this El Niño are quoting a real number. The conclusion they are drawing from it is not supported by that number, and NOAA said so in the same sentence. 2 specific patterns of misinformation have emerged in the coverage of the 2026 event. They are not products of malice. They are products of speed. News outlets need to publish quickly. Scientific documents are dense. The translation from one to the other introduces errors. 2 errors in particular have appeared repeatedly, and both of them are worth addressing directly. The first error involves the framing of the strong or very strong probability. Multiple outlets have reported the 37% number in headlines that imply a strong El Niño is the likely outcome. The framing varies. Some headlines say strong El Niño now considered most likely. Others say 1 in 3 chance of historic event. Still others package the 37% next to the word probable, in ways that suggest more than half the chances are on the strong side. What NOAA actually said in the May 14th diagnostic was that no strength categorization exceeded a 37% chance. That is not the same as saying a strong El Niño is likely. It is the opposite. It is saying that no single category, including the moderate category, which is the highest probability, gets above 37%. The headline that says strong is likely has inverted the meaning. In probabilistic terms, 37% is less likely than the flip of a coin. It is less likely than the moderate outcome. It is less likely than the combined weak and moderate outcomes. The phrase in the document was a statement about the spread of the probability distribution, not a forecast that the upper end of the range was the central expectation. The reporting that turned that spread into a strength forecast misunderstood the math. The honest reading of the May 14th document is that the most likely individual outcome is moderate El Niño, that the next most likely outcomes are weak and strong in some order depending on how the next update goes, and that very strong remains a real but minority possibility. None of those 4 outcomes is above 50%. All of them are live possibilities. The distribution is genuinely wide, and the news framing that picked the right tail of the distribution as the central forecast is reading the numbers backwards. This matters because it shapes what regular people think the next 12 months will look like. A reader who absorbs the headline framing comes away believing that a super El Niño is on the way and may make decisions, financial decisions, planting decisions, water purchasing decisions based on that belief. The belief is unsupported by the document itself. The document says strong is one of 3 plausible outcomes, and the other 2 are still more likely combined. The second error is structurally larger. It involves the comparison between the 2026 event and 1997 to 1998. As discussed in Part 3, the measurement tool changed in February of 2026. The 1997 ONI peak of plus 2.4 degrees Celsius was measured on the old ruler. The 2026 numbers in NOAA's current operational framework are being measured on the Roni, the new ruler that adjusts for background warming trends in the Pacific baseline. The 2 indices are not directly comparable. The Roni adjusts for warming trends that the original ONI included as part of its signal. A 1997 ONI value of plus 2.4 does not translate to a 2026 Roni value of plus 2.4. The exact conversion depends on the specific period being compared and the background state of the tropical Pacific. NOAA has not yet published a formal retrospective table converting major historical ONI peaks into their equivalent Roni values for general public use. The conversion exists in technical literature, but it is not in a form that allows a casual reader to look up the 1997 peak and instantly compare it to the 2026 forecast. Yet headlines continue to compare the 2 events as if the numbers are interchangeable. Comparisons to 1997 are appearing in stories about 2026 forecasts that quote Roni framework probabilities. The benchmarks are not comparable. The comparison is structurally invalid, and no outlet has explicitly said so. This is not a conspiracy claim, it is a structural observation. The index transition was published in NOAA's NWS Public Information Statement 2605 in February of 2026. The technical literature on the difference between ONI and Roni exists. The information is publicly available. The problem is that news cycle speed and scientific communication speed operate on different timescales. The reporters covering the May 14th diagnostic were writing stories on a deadline of hours, not days. The careful work of translating the new measurement framework into accessible public terms takes weeks or months of effort by NOAA's communications team and outside science writers. That work has not yet caught up to the speed of the news cycle. The result is a country reading 2026 numbers through 1997 glasses, comparing the 2 on the assumption that the magnitudes mean the same thing, when in fact they have been measured by different instruments with different methodologies. What does a responsible reading of the data look like? It looks like reading the actual NOAA document, not the news summary. It looks like noting the probability distribution and not just the headline emergence number. It looks like acknowledging that comparisons to 1997 are structurally limited until a formal conversion table is published. It looks like watching the next several monthly updates to see whether the trajectory accelerates or holds. It looks like recognizing that uncertainty is not a failure of the forecast. Uncertainty is what the forecast is actually saying. The probability distribution is the message, not the headline number alone. The errors are not products of bad faith. They are products of the gap between how science is produced and how news is distributed. Closing that gap requires patience on both sides, more careful translation by science communicators, and a willingness on the part of news consumers to read past the headline into the actual document. The document is online, the methodology is public, the honest reading is available to anyone willing to spend 20 minutes with the source material. Here is where we actually are. El Niño is almost certainly coming. Its strength is genuinely uncertain. The historical comparisons being made are technically invalid, and 3 honest readings of the same official data produce 3 very different pictures of what the next 6 months look like. Part 12 walks through all 3. Part 12, 3 Ways to Read the Same Ocean. There are 3 honest versions of the next 6 months. NOAA has put numbers on all 3. Tonight we're going to name them, weight them, and tell you exactly what to watch for between now and October. The first reading, the most likely one carrying roughly 60% of the probability weight, looks like this. El Niño arrives as a weak to moderate event. California gets above normal winter precipitation, enough to partially refill reservoirs and rebuild Sierra snowpack toward normal. Lake Powell moves from 24% capacity into the mid-30s, not full, but the largest single-year recovery the basin has seen in years. The Pacific Northwest gets a drier than normal winter. Fire risk rises through 2027 but does not hit record territory. The Atlantic sees moderate hurricane suppression. The Gulf Coast and Southeast get a wetter winter with some flooding risk. No region sees a historically extreme outcome. The season is measurable, real, and manageable. That is the central forecast. It is not the only one. But here is what the first reading and the second reading have in common that neither headline has said clearly. Both of them produce a winter of above normal precipitation for California. One produces manageable above normal, the other produces a version that strains infrastructure. The difference is not in the direction, it is in the magnitude. And magnitude is exactly what is still unresolved. The second reading is the elevated concern reading. NOAA's probability distribution allocates roughly 30% of the weight to outcomes in this range. The second reading says the coupling accelerates. The June 11th probability distribution shifts toward the upper end, and the event tracks toward an only peak in the plus 1.5 to plus 2.0 degrees Celsius range. That puts the event into strong El Niño territory, but not into the very strong range that defined 1997 and 2015. Under the second reading, the California impacts amplify. The winter of 2026 to 2027 brings significant flooding risk to the central and southern parts of the state. Atmospheric river sequences arrive but do not lock in for the entire season. The northern Sierra snowpack rebuilds aggressively. Reservoir refill is robust. Lake Powell moves toward 40 to 45% capacity, which is still below long-term averages, but represents the largest single-year recovery in years. The drought picture for the Southwest improves materially. The Pacific Northwest, under the second reading, faces a more difficult winter and a worse subsequent fire season. The teleconnection pattern locks the storm track south of Oregon and Washington. The forests enter their next fire season with worse moisture deficits. The fire risk in the summer and fall of 2027 is high. The Atlantic Basin, under the second reading, sees substantial hurricane suppression. The named storm count drops well below recent years. The number of major hurricanes reaching the United States is meaningfully reduced. The Gulf Coast and Southeast, under the second reading, see persistent winter precipitation. Flooding risk along the lower Mississippi rises. The pattern is wetter and cooler than recent winters, but not unprecedented. The third reading is the worst case. NOAA's probability distribution allocates roughly 10% of the weight to outcomes in this range. The third reading says full coupling produces a super El Niño with Oni or Roni values approaching or exceeding the 1997 to 1998 benchmark. The teleconnection impacts are disproportionately amplified relative to the second reading because of the nonlinearity in atmospheric response. Under the third reading, California experiences a winter of repeated atmospheric river sequences. The jet stream locks south for weeks at a time. Storms arrive in succession. Flooding becomes catastrophic in coastal counties and in the Central Valley. Reservoirs overflow. Mudslides close major highways. Infrastructure damage runs into the billions. The Pacific Northwest, under the third reading, experiences extreme drought through the winter and into the following summer. The storm track stays south. Snowpack in the Cascades collapses to record lows. The wildfire season of 2027 sets new records for area burned. Air quality across the region deteriorates dramatically. The Atlantic Basin, under the third reading, sees record hurricane suppression. The named storm count may drop to levels not seen in decades. Major hurricane landfalls in the United States may be eliminated or nearly so. This is the one impact category where the third reading is, paradoxically, good news for the populations affected. The Gulf Coast and Southeast, under the third reading, see substantial winter flooding, persistent storm passage, and water management challenges that strain infrastructure designed for less extreme patterns. Across all three readings, the indicators that would push the picture from the first reading toward the second or third are specific and watchable. The first is the June 11th SOI value. If the SOI has plunged into strongly negative territory by then, coupling is engaging. The second is the July NOAA update, which will incorporate the June observational data and will show whether the strength probability distribution has continued to shift toward the upper end. The third is the first weekly Niño 3.4 readings in August, which will indicate whether the surface response is on track for a strong peak in the fall and winter. None of these indicators delivers a single yes or no answer. Each of them moves the probability distribution. Each of them narrows the uncertainty. By the time the country reaches October, the picture will be much clearer than it is today. But today, in early June of 2026, the honest answer is that all three readings remain in play, with the first reading carrying the most weight by a substantial margin, and the third reading carrying real but minority probability. The one thing all three readings have in common deserves direct attention. Across every scenario, weak, moderate, or very strong, the summer of 2026 in California is already decided. That truth was established in Part 7. The winter of 2026 to 2027 belongs to the forecast. The summer of 2026 belongs to the drought. No update on June 11th, July 10th, or any date after that changes what the Central Valley is going through right now. Consider a retired couple living in Scottsdale, Arizona. They are long-time desert residents. They moved to Scottsdale in the early 2000s and have lived through every drought year of the past 2 decades. They understand exactly what Lake Powell means, because they have read the local newspaper coverage of the Colorado River Compact for years. They check the United States Bureau of Reclamation reservoir level page on their laptop the way they once checked their retirement account balance. Not panicking, just watching. They have watched Lake Powell go from full in the late 1990s to 24% capacity over the course of the past 2 decades. They remember when the boat ramps that are now hundreds of feet from the waterline used to reach the water. They know the number that matters is not the one in the news headlines. It is the one on the gauge at Glen Canyon Dam, which the Bureau of Reclamation updates daily. They have learned to read the data themselves. They have learned that the news framing of any given week tells them less than the actual gauge reading does. They have made their peace with what watching the data feels like. It is not exciting. It is not panicked. It is the steady act of paying attention to something that matters and that is taking its own time to resolve. The 3 readings disagree on how bad the winter gets. They agree on one thing. The summer, for a lot of Americans, is already decided. Part 13. The ocean does not care about forecasts. In 6 days, a document will appear on a federal website in College Park, Maryland. It will be 4 to 6 pages long. It will include a probability distribution, a discussion of the latest observational data, and a formal assessment of the current state of the Pacific. It will be read by thousands of forecasters, planners, and water managers the same morning it is published, and most of the people whose lives it describes will never know it exists. That document is the latest entry in a record that has been kept, with increasing precision, since the early 1980s, and the cycle that record documents has been running for thousands of years before any instrument measured it. The El Niño Southern Oscillation did not begin in 1997. It did not begin in 1982, when the modern monitoring framework was built. The cycle has been running for at least 5,000 years, long enough that pre-Incan coastal communities left evidence of it in their fishing patterns, in sediment cores, in the fossilized bones of anchoveta in archaeological sites that predate written history. The instruments are new. The cycle is ancient. What changed in the late 20th century is not the cycle. The cycle was always there. What changed is humanity's ability to watch it. The 1982 to 1983 El Niño caught the scientific community by surprise. The instrument network at that time was sparse. The forecasting models did not yet include adequate ocean coupling. The event happened, and the consequences were severe, and the world was not ready. The 1997 to 1998 event happened, again with consequences, but this time with a far better monitoring network that captured the development in nearly real time. The 2015 to 2016 event happened, and the network had improved again, and the methodology continued to refine. Now the 2026 event is happening, and the monitoring is denser still, and the methodology has been updated again, with the Roni replacing the Oni to better isolate the variability signal from the background trend. That last update raises a question the data has not yet been able to answer. The Roni exists because the background state of the Pacific has been changing. The 30-year baseline that the Roni used was becoming a poorer reference point as the ocean's resting state warmed. That warming is documented. The trend has been measured by every major oceanographic agency in the world. The Pacific today is, on average, warmer than the Pacific of 50 years ago, and the trend has been more or less continuous through that period. If the background state of the Pacific has shifted permanently to a higher energy regime, then future ENSO events will be initialized from a warmer starting point than any event in the historical record was. The Kelvin waves of the next century will be loading their heat into water that is already warmer than the water their 20th century predecessors loaded into. The teleconnection signals will be reaching an atmosphere that is already warmer than the atmospheres of past events. The historical analogues we have used to understand each new event may become progressively less useful as the baseline state of the system drifts away from the conditions those analogues were measured in. Here is the part that does not change regardless of what the June 11 document says. The Kelvin wave currently crossing the Pacific has already committed its energy. It cannot be recalled. It does not wait for the probability distribution to resolve. By the time NOAA issues its June 11 discussion, by the time its July discussion follows, by the time the October peak reading arrives, the wave will have already completed most of its transit. The question of how strong 2026 becomes will be answered by a physical process that is already in motion. The forecast does not steer the wave. The forecast only describes where the wave appears to be going. This is not a catastrophist claim. It is an honest scientific question that NOAA's own index transition implicitly raises. By adopting the Roni, the agency acknowledged that the old reference state was no longer matching the operational reality. By isolating the variability signal from the trend, the new index gives scientists a cleaner read on how unusual each event is relative to current conditions. But the trend itself, the slow shift in the baseline that necessitated the new index in the first place, is a separate question, and it is the larger question. The June 11th update will not answer that larger question. The July update will not. The October update will not. The strength of the 2026 event, whether it lands in the moderate range or pushes into territory comparable to 1997, will eventually be measured and recorded. But the question of whether the Pacific is now operating from a baseline that no past event was initialized from, the question of what that means for the next event after 2026, and the one after that, those questions are slower questions. They take decades of additional data to resolve. What this video has been about is an event, a specific Kelvin wave, a specific set of probabilities, a specific 6-day countdown, a specific set of regional impacts. The event is real. The numbers are NOAA's numbers. The uncertainty is genuine. The mechanisms are well understood. The unknowns are clearly stated by the scientists watching them. None of that is in doubt. The viewer who has watched this far now has a better set of questions than they started with, and a clearer sense of what to watch for in the documents the agency will publish in the coming weeks. But underneath the specific event is the longer cycle, and underneath the longer cycle is the slow drift of the baseline, and the act of watching all three at once, the event, the cycle, the drift, is the act of reading a message that the ocean has been writing for longer than any human civilization has existed. The opening of this video described something the size of a continent moving at the bottom of the Pacific Ocean. That image was meant to convey urgency. It was meant to say that something specific is happening right now, and that the country should be paying attention. It is true, the Kelvin wave is real, the subsurface anomaly is real, the June 11th countdown is real. But the image carries a second meaning, and that second meaning becomes clearer as the video closes. The thing moving at the bottom of the Pacific is not new. It is the latest iteration of a movement that has been happening in slightly different configurations, in slightly different magnitudes, throughout every human generation that has ever lived along that coast. The instruments are new, the probability distributions are new, the methodological updates are new, the movement itself is ancient. The Pacific does not care whether the headlines get the comparison right. The Kelvin wave will travel at its own speed, the thermocline will tilt as the wind tells it to, the trade winds will hold or release as the pressure gradient dictates. None of that responds to forecasts. It responds only to physics. The act of watching is a human act. The instruments, the buoys, the satellites, the weekly diagnostics, all of them exist because after the 1982 surprise and the 1997 wake-up call, the agencies of the world decided that watching this cycle carefully was worth doing. Not because watching changes the cycle. What watching changes is what people can prepare for in the months before the worst arrives. The grandfather in Chimbote in 1997 did not have the benefit of that watch. The farmer in Fresno County in 2026 does, even if he does not always know how to read the document. The data already in hand has answered the first question. The Pacific has changed state. The basement is loaded. The next phase is uncertain, but the system is moving, and the country, whether it knows it or not, is already inside the event. And somewhere, 200 meters below the surface of the equatorial Pacific, the wave continues east, the way it has done in every generation that has ever lived along this coast. The watch continues. Whatever the next 6 days bring, the data already in hand has answered the first question. The Pacific has changed state. The basement is loaded. The next phase is uncertain, but the system is moving, and the country, whether it knows it or not, is already inside the event. The instruments will keep working. The diagnostics will keep being published. The probability distributions will keep narrowing. And somewhere, 200 meters below the surface of the equatorial Pacific, the wave continues to travel east, the way it has done in every generation that has ever lived along this ocean, in the language the ocean has been writing for longer than civilization has existed, while the watch, quietly, continues.